Welcome everybody to one of our award-winning best paper sessions. So our speaker today is Simon Wright, who people who've been to any of our big events, any of our annual systems engineering conferences over the last, I would say, decade or so, will certainly have seen Simon, certainly have met him. We were just chatting before. I was convinced this paper was from about 2 years ago. It turns out to be from 5 years ago. So we were just saying that's what the pandemic does to you. Simon, many of you will know. For those of you that don't know him or haven't met him before, Simon will be taking over in a moment. I'll get him to give his full sort of background then. You might recognize his name, even if you've never seen him, from this excellent Don't Panic book, The Absolute Beginner's Guide to Service Systems and Services, which came out last year. There's also an online video talk about this as well, talking about the book, where I interview Simon and he tells us all. We're here to talk about two things that are sort of close to my heart. So it's, like I say, it's a paper that won, I think it was best paper in 2018, and there's two topics in it that are very close to my heart. There's artificial intelligence, which is of course a very hot topic at the moment, because clearly it's only ever been used in the last 6 months, if we believe the current media. It's actually many years ago, over 30 years ago, my original doctorate was in AI, so I've got there's a space in my heart for all things AI. So and I remember when I saw this paper, I was very impressed by it, but also obviously for me the MBSE side of things as well. And there's some excellent natural language processing using MBSE style techniques, and something that, you know, many of us have been using for a while. So very powerful, I think massively underused technique. So without further ado, I'm going to hand over to Simon. The paper is called Using the AI Technique of Natural Language Processing to Develop Technical Specifications for Military Vehicle Procurement. That just flows off the tongue. So Simon, I will hand over to you, and we'll come back to you with some questions.
First of all, thank you, Incosi UK, for suggesting that I reprise this talk, as you say, 5 years ago. I've looked through it and I still find it very prescient, which is, but of course I would naturally. I've been a systems engineer. I looked it up the other day. For 40 years, I've had the title of systems engineer, and I've covered lots of different systems, lots of different domains. This is some work that I did back starting 2014 through to 2019. And it brought together a lot of the tools and techniques that I'd learned over the many years into one cohesive whole. And that's really what I'd like to talk about, plus that extra twist of natural language processing as well, an AI technique that is underused in my view. Anyway, let's go and look at some topics, says he, pressing the wrong button. So I'm going to start off with giving you some context to this presentation. What's it about? Then I'm going to look at how we analyze for stakeholders, how we looked at life cycle states, we looked at system context diagrams, and then that led into functional analysis. And all this work was stored into a knowledge base using natural language modeling. This was very useful because we also were able to come up with the quality metrics using the same natural language modeling. And as a result, when we wrote requirements, we were able to combine all this with a natural language processor to give us quality measurement. How good were our requirements? And then this was used iteratively to improve our requirements expression over many months, so that when we issued our technical specifications, we knew that we had a very good chance of actually communicating all our ideas to the bidders. So this is about a self-propelled gun for Norway. And in 2014, they were looking at a new gun. These were the 4 bidders. And in order for them to bid, we developed, as you can see on the left-hand side, an architectural description, so that we described what we were looking to have in architectural terms. We then had a very detailed system specification. Then we had our initial maintenance and training program, another specification. The fourth specification was the 25-year logistics support, and a statement of work saying how, in systems engineering terms, we expected our suppliers to develop and deliver. So that's the background. It's very prescient as it was, because these were delivered back in 2019. And guess what? We're in the middle of an artillery war in Ukraine. But before I go any further, I must thank the Land Division of the Norwegian Defence Materiel Agency. They've allowed me to present details of this work at a very informative level, and it was all to do with Project VDAR. VDAR is the Versatile Indirect Artillery System, and I thank them for allowing me to share this material yet again with you. So we needed a strategy to do all this work, and the strategy was that we were going to use structured and a systematic approach using models which promoted effective work. We had quite a compressed time scale. So anything we did, we had to do effectively at a high quality level. We then were going to have frequent reviews, a plan, do, check, act. And we were doing this on a 2-weekly basis. And this idea of a plan, do, check, act with 2 weekly reviews to catch problems early, I believe there's a modern term for it. I think it's called agile. But it's a very old technique. It goes back many moons. It's just got a new name in my view. Anyway, that's what we did, plan, do, check, act. Because none of those systems were coming from a country where the, sorry, was there an interruption there? Where the language was not English. So the Norwegians, the first language is not English, as well as the 4 bidders. We were going to concentrate on diagrams and lists to allow us to communicate this common understanding in English and to achieve that quickly. And we were also going to use structured English and quality criteria to drive the requirements expression from a stored knowledge base. So I'll explain how that goes through, how that was achieved. So, stakeholders. This is the 15288 definition of stakeholders, and they identify operators and users. And in my humble opinion, that's far too broad a definition for use in requirement specifications. And so I tend to use a different technique. It's called the onion model. It was first described by Ian Alexander in 2006. And I'll just take you through how that works. There's 4 levels. First of all, we have the product or the service, and that contains no stakeholders. Around that, we have the system of interest. And of course, the system of interest is the product or the service, plus the people who either operate the product or deliver the service, and includes things like training, support, maintenance. So that's the system of interest. Now, outside of that, is what is referred to by Ian Alexander as the containing system. The containing systems are those who are immediately benefit from the functions carried out by the system or who interface directly with it. And outside of that is the wider environment. Now, these are people who are affected indirectly, who, if you like, derive benefit rather than actually are functional beneficiaries, or induced harm, things that could harm people by the use of the product or the system. That's the generic 4 levels. And then Ian Alexander gives us various generic stakeholder roles. He sees them as being beneficiaries, having a negative impact, being regulatory, operational, or experts. And within each of these roles, there's a set of additional sub-roles: functional, financial, or political beneficiaries. Regulatory could be enforced or voluntary. Operational could be human operators or a neighboring system. And so for each of these individual stakeholders, we need to allocate them to somewhere in that onion diagram. And this is what he suggests we do. For the system, these are those who actually physically interact, touch the product or the service. So you've got the normal operator, the maintenance operator, and operational support. They are intimately involved with the product to develop the system. Remember, the system always involves a person if there's an operator or something like that. Now, within the containing system, we've got very importantly the functional beneficiary. Hopefully you can see my cursor. Those who benefit from having the system, they may not actually touch it, but they may actually tell the normal operator what to do. Very importantly, obviously, is purchasers and sellers and any interfacing systems. And in the outer circle, the outer layer, we've got things like the financial beneficiaries, political beneficiaries, the public, regulators, and very importantly, negative stakeholders. Now, I know this is a military system and that was going to be the enemy, but for any system, there's always going to be negative stakeholders. If it's a product, there may well be competing products, and the competing product developer doesn't particularly want your product, which will be better and cheaper, to go on the market. So there's always going to be negative stakeholders. So that's how we map roles onto levels. What are the ones that we have for this self-propelled gun? Well, the normal operators we found out were a commander, gunner, driver, loader, and a remote weapon system operator. There are various others as well. These are the main highlight ones. We have operational support, we have maintenance operators, and the various subsystems that they support. Now, very importantly, we defined that the commander was the term to be used as the person in charge of the gun. A lot of people say, well, that's the captain, or that's the major, or that's the head or lead. And no, it's very simple. If we ever want to refer to the normal operator, they have to use the word commander. That's the only valid for this project. That's the only valid name for the person in charge. Similarly, the person who fires it is the gunner, and it's not the firer or the deputy commander or anything like that. We are defining specific roles for our stakeholders, which shall be used throughout the length of this particular project. So what does this actually give us, having identified stakeholders? Well, it gives us what we call the subjects for requirement statements. So immediately we can begin looking at stakeholder needs. The commander shall give commands to whoever. The loader shall load the gun. The gunner shall fire the gun, those sort of things. So we've got a set of subjects that we can start writing our stakeholder requirements. The outcome is we now have a shared understanding. When we use a particular word, that's what we mean. When we identify a particular person, a stakeholder, we should have now a shared understanding of who it is we're talking about. And we end up with a list of all the stakeholders and a class diagram for those stakeholder roles. And we entered these into a knowledge base. We had a particular tool that we were using that could do the natural language processing for us. And it operated on a knowledge base. So let's have a look inside the knowledge base. You could get a list of all the stakeholders, or we could have a diagram for all the stakeholders. And this is really important because let's take, for example, functional beneficiary. For non-English speakers, it may be very unclear what a functional beneficiary is, but it's very clear as to, in the diagram, that it's people in the battery, in the battalion, in the brigade, in the army, NATO, etc. So it's very important that lists and diagrams are more easily understood by non-native language speakers. Not to say that just because we speak the same language, English is spoken in America and in the UK and in Australia, but actually different words have very different meanings. So we clearly define what we mean by operational support. It will deliver various resupply functions. So that's our stakeholder. This is just an example out of the knowledge base, and all the stakeholders were entered in. Now we could look at life cycle in the operational state. So this is the operation, these are life cycle states of the gun as you can see, and it starts with the stored state. Normally these guns are stored in country, And because it's self-propelled, it could come straight out and start becoming operational. But in general, they have to be loaded onto a transporter and taken to the operational environment where it is then unloaded and it becomes operational. While it's being operational, it might need a bit of maintenance. There might be a local maintenance area which you can drive to, or it might have to get back on the transporter, get to a main depot and go and be into the maintenance shed. Whilst it's operational, apparently sometimes they get driven into ditches and get stranded or stuck on a tree or stuff like that, in which case they need to be recovered. And then a recovery vehicle will be attached to them. It'll then be towed, or typically to a maintenance department to check there's no damage, or just simply out the ditch and it's then unattached. And the importance about this is we're starting to really focus in on, again, this controlled vocabulary. We've defined states and we defined actions. When operating, the SPG shall. When stored, it shall. When it's attached, when it's loaded. And what we've got is a shared unambiguous understanding. By unambiguous, I mean that if you use the word, the SPG shall be loaded, we're not loading a shell into the gun. The SPG is always loaded onto a transporter. It's never attached to a transporter. It's only attached to a recovery vehicle. So there's a subtle difference between loading and attaching, which is valid throughout this project. And we clearly explain to people via diagrams how that shared understanding is achieved. So we've now got a list of life cycle states, a list of actions, and again, all of these were put into our knowledge base. So how does that look? Well, the states, there's the various list of states, but more importantly, we've now got some verbs. We had some nouns, we've now got some verbs: attach, load, scrap, self-propel, etc. So we can start actually building up some sentences now. We've got nouns and verbs. And the way we do that is we look at context diagrams in each of the individual states. Now, when we start with context diagrams, I always like to start with the simplest. And the simplest is when it is being attached to a transporter, because all you're worried about is the mechanical attachments of the vehicle to the transporter. It could be by air, road, rail, or sea, but still those mechanical attachments have to be provided. So that's that's the simplest. The next simplest is probably the stored. These vehicles are stored in Norway during the winter. It could be minus 28 degrees C there, or even colder. I've only experienced minus 28 whilst I was out there. As a result, you need dry air to be circulated so you don't get condensation into the electronics, which will work at low temperatures, but not if they're damp. And you also need some electrics just to keep certain elements ready, trickle charging the batteries, stuff like that. So again, very simple. We've defined the parking bay to vehicle interfaces. Finally, we have disposal. And the plan is that they will be broken out into components and disposed of as individual components. We never thought about actually having to deploy them to another country, but then that was 2018 and we didn't have a war on our hands. So those are the simplest states, and it got people used to having a context diagram so that when we needed to come to something a little more important, they understood what we were doing. Yes, these were simple, but they're not trivial. It's very important, for example, that we have that dry air, otherwise the system is not going to work. Notice that the crew in these particular three are not part of the system. If it were, we would have depicted it on the diagram. Here is something a little more interesting. This is the recovered state. Note, first of all, the possibility of opposing systems. You may be stuck in a ditch somewhere, and if the enemy sees you, they're going to fire at you. You can only fire back using the machine gun, the remote weapon system. You can't use that dirty great big gun if you're in a ditch, at 45 degrees. That would be very dangerous. So there's a limited response that you've got. Notice also that the crew is part of the system. The crew can be in the vehicle when it's being towed out by the recovery vehicle. And notice there's a second type of mechanical attachment. Now, this immediately throws up the idea, well, is that the same mechanical attachment for loading and unloading from the transporter? What are the mechanical forces needed to pull a vehicle out of a ditch? Are they the same mechanical forces that need to secure this vehicle on a train, an airplane, etc.? So this is, again, finding this commonality was really important for our development. So that's the recovered state diagram. What's the next state? Well, we're going to look at the maintained state. It's a little more interesting. Now we've got enabling systems. We've got the parking bay, again, because they will have parking bays in the maintenance sheds and with interfaces. We also have cranes and jacks as well. So there's a third type of mechanical attachment. And again, we need to explore the possible commonality between this and the transported and recovered state, because if we have one mechanical attachment that can cover all areas, it's going to reduce the possibility. If you had two mechanical attachments, one for the crane, one for the recovered state, then you might use the wrong mechanical attachment, and with different forces, you know, you could drop the crane or leave it stuck in the ditch. So we had to very carefully consider the possibility of having a single set of mechanical attachments. Notice there's a commonality with the stored state. Lo and behold, we've got dry air and electrics. Is this again the same interface as we had before? Ideally, it should be the same. If we can reduce the number of interfaces rather than having special ones for maintenance bays and storage bays. And also, there's a commonality with the recovered state. We've got electrics, hydraulics, and compressed air. So using these diagrams, it was very clear to understand that there was a lot of commonality of interfaces, and we had to make sure that when we specified interfaces, that we covered all the possibilities. So that's the maintained state. Excuse me while I take a sip of water. So what about the operational state? You see, everybody was interested in going to this one first, and I delayed it to the last because you build it up diagram by diagram, because this was the first time they'd used this approach, and the people I was dealing with were able to much better learn how to develop things like context diagrams. What's the first thing we notice? The variety of opposing systems. There might be chemical, biological, radiological, nuclear. We may be shot at directly by small arm fire. We might have an indirect incoming shell. This is the interface that is happening down in Ukraine, the artillery war. Mines, yeah, those are around, IEDs, and there's other threats like EMP and laser. So there's a variety of opposing systems, and what this leads to is we need protection requirements. We need to protect the crew because look, the crew is in there, so we need to protect them from all these different types of attack. Note the variety of enabling systems. The crew does have some maintenance, but actually they might have to bring in some extra spares and special tools whilst operational. You might run out of ammunition, so there's going to be ammunition resupply. And look, there's lots of different types of ammunition that is needed. There's fuel resupply, which also includes lubrication and coolants. And also, you may be operational for days on end. So you're going to need water and food. Well, if you put water and food inside, guess what comes out? Waste. Now, you have to consider that. I mean, if you don't consider that, if you get that interface, the crew are sitting there eating, get desperate for the loo, where they're going to go to the loo. So yes, enough said about that, but that's a really vital, there's an input, there's a corresponding output, you need to take care of it, the waste requirements. So this was presented to the stakeholders which were identified right at the beginning. We said all these different operational states, sense? Have we missed anything, etc.? And what came back was yes. A lot of the domain experts that I spoke to talked about integration of systems that don't feature on that context diagram, nor in that stakeholder diagram. Oh dear. So the system of interest from a stakeholder's point of view was actually incomplete. There was something we had not identified, which we really needed to identify. And that was another set of systems, the owner of the interfacing systems. And we had to go back, and this typical iteration where you do some work and it gives you light on, it exposes what you've done previously to a different light, and you see something new. Typical with this plan, do, check, act loop. So interfacing systems. We discovered actually we'd missed a new state, which is the purchased state. And if we hadn't have gone forward with this, it would have been a complete disaster, because this is the purchased state, that all of these pieces of these subsystems, the machine gun, the intercom, radios, the camera, the GPS receiver, the computers, the security functions, etc., ammunition, the existing camouflage systems, all of these existed already. This thing in the middle is what we were buying. We had to explain to our bidders that we're going to buy this, and they're going to have to fit all this existing equipment. And therefore we had to develop interface control documents for each of these government furnished equipment, this GFE. So what's in the interface control document? It had to cover the space that was needed, the mechanical fixing of these pieces of kit into or onto the vehicle. Were there any power requirements? If they were, how they were going to get them? What was that power? Was it electrical or was it hydraulic power? Was there any cooling requirements as well? And where was that going to come from? Was there any analog or digital data that we needed to worry about? So we had to develop for every single one of these interfaces an interface control document that clearly defined to the bidders how they were going to have to integrate these elements into the overall system. So what was the result? Result was that we have a full system context. We can start writing requirements like the SPG shall provide these outputs. The SPG shall protect from these threats. The SPG shall receive these inputs as well. So these diagrams are used to direct the expression of the requirements. And what we've got is a really controlled vocabulary. We have names for everything, and they are unique names for everything, which is really important, particularly when English is not your first language. We've got the list of interfaces. We also have a list of functions, the top level functions that this system needs to do. And also, suddenly, it came up that there's this other vehicle. I can remember the day the project manager came in and said, "Oh, Simon, we like the self-propelled gun. Could you do the same for the ammunition resupply vehicle?" I said, what's the difference between an ammunition resupply vehicle and a self-propelled gun? I'm expecting it to be huge. And he said, "Oh, no, it's very simple. That shells come out of the gun at 1 mile per second, but they only come out at 1 foot per second from the ammunition resupply vehicle. But otherwise, they're virtually similar." So when we actually then took a close look at the needs of the ammunition resupply vehicle in all the various life cycle states that it would have to exist in, this was obviously the most complicated, and we were able to quickly swap ammunition resupply vehicle in the middle with self-propelled gun now on a cooperating system. And you can see there's a huge amount of commonality between the two. Same sort of inputs. In fact, I think all the inputs are virtually the same. And some of the outputs are shared as well. So we were able to write a second system specification for the ammunition resupply vehicle relatively quickly by identifying the commonality of the interfaces with the SPG. So I talked about having functions. What functions were they? Well, these are all the primary and secondary functions that were identified. So while operational, the SPG can be self-propelled or stationary. It needs brakes. It's going to communicate and engage with targets. It's also got to be rearmed, refueled, recovered, transported, maintained, etc. What's important about this is when we came to define the RAM, the reliability, availability, and maintainability requirements, because they were having a big problem trying to define them. But once we had got all these functions, and we've actually allocated them as either primary or secondary functions, we could say, well, a critical result is the loss of one of the primary functions. If it can't do one of these things, it's not doing its main job. If it loses the ability to be recovered, well, that's a pity, but it's not a primary function that it can be recovered. And critical errors were then, we could then say, right, so many critical errors, you know, the maximum, I can't remember the exact requirement, but something like there can only be 4 critical errors per year, per 10 years, I think it was. And so what is a critical error? The loss of one of the primary functions. So we can now, having got the system defined, we can now look at subsystems. And the subsystems of the SPG diagram in the knowledge base, the crew, the platform, the C4I system, main weapon, light weapon, and safety systems. We could also add physical attributes like weight and height, referencing cooperating systems, and all the functions. And this allowed us to then drive our requirements expression from the internals. So we could say the main weapon system shall fire so many rounds for so long. The SPG shall engage in targets so far away. Maximum weight of the SPG, really important for the transportation and recovery requirements. We've got a clear definition of these critical errors, so we can get our reliability, availability, and maintainability requirements. We've got a list of functions and subsystems and system properties. We're driving the expression from the diagrams, but we can then go further down into the structure of the SPG. We've got the self-propelled gun with all its bits, and here are the crew, the C4I system, and they've got the same types of attributes, parts, physical attributes, functions, etc. And how do we then proceed? Well, it's quite simple. We have the recursive application of those techniques that I've talked about, and by recursively applying them, we enable a logical and physical and functional breakdown of the system down to an appropriate level. We didn't quite get down to every element, but every aspect that we needed to in order to specify unequivocally what it is we wanted to buy. The result? Well, this structure means we've got detailed requirements. The main weapon system the gun shall fire. The light weapon system, the machine gun, shall engage certain threats. So we've got detailed subsystem requirements dropping directly out using the same methodology. We've got a detailed common understanding, again, unique definition of our verbs and nouns. And we've got a list of subsystem functions, subsystem components, and guess what? They're all stored in the knowledge base. And we were able to develop those 5 detailed specifications. Great, but how do we know that our requirements made sense? What was the quality of our requirements? Well, for me, a technical specification has to be precise, accurate, and unambiguous. So what do I mean by that? Well, precision, I believe, is a function of completeness. Because if you've missed a requirement, then the specification is imprecise. You haven't covered everything you need to cover. Accuracy is a function of correctness, because if you've incorrectly expressed a requirement, then that requirement is inaccurate and you won't get what you need. And finally, the unambiguity is a function of consistency, because if requirements use terms inconsistently, then different readers are likely to have different interpretations and therefore develop different solutions. and solutions that don't meet the need. So I'm going to now look at how we might do that. Well, a correct requirement for me, it looks at textual analysis, syntax analysis, and semantic analysis. A complete set looks at incompleteness by comparison with the knowledge base, incompleteness between high and low level specs, and consistent, well, we look for redundancy and inconsistent use of terms, units, and properties. Now, I don't have time to go through it all, so I'm just going to look at correctness to show you how we can use natural language modeling and an AI tool to come up with a correctness metric. I'm going to look at textual analysis first. What do I mean by that? Well, we can all spot poor requirements. Here is 5 requirements which are poor. These are actual requirements, not from this project, but from other projects. I collect bad requirements. I'm that sort of nerdy. My favorite here is number 3. I can remember distinctly reading the requirement, appropriate standards shall be used when necessary. Now, it's very easy to spot badly phrased requirements because they often contain these key indicators, specific words, constructs, or phrases which hint at the poor quality. And it's not difficult to define a set of terms to avoid as follows. So here in red, all the things that need to be changed, terms which tell us that it's poor, appropriate, necessary, careful, same, sorted, relevant, all those sort of things. So notice that we can now calculate a metric of how poor they are. 5 words are needed to be changed here, 6 there, 3, 4, and 1. Now, I'm going to define a correctness metric, a measure of how correct it is. It's the number of times a word or phrase occurs in a requirement, which is in the avoid list. Now, if the quality score is 5 or more, then that's a low quality requirement. If it's 1, 2, 3, or 4 words to avoid, that's medium. If there aren't any, less than 1, 0, then that's high quality. That's my low, medium, and high criteria. And we can now measure. Let's say that we've got our requirement spec. These are our 5 requirements. We've got a total of 19 words that need to change, an average of 3.8 per sentence. This is a pretty low quality set, but we can we've got a number to associate with it. And the benefit for that, I will show in just a moment why it's useful to have a metric on the quality of your requirements. But I've only dealt with correctness. I need to look at the other aspect, the syntax analysis. And syntax analysis is in addition to the textual one. So here are the low, medium quality requirement. And on the right, how I would have rephrased it. Rather than it will implement, the specific version of the software that shall implement the same set of functions that were implemented in the other version. Relevant sets of project data. This was actually 10,000 British town names shall be alphabetically sorted in less than 5 seconds. Appropriate standards, ISO 12207, shall be used throughout the life cycle of development projects. So here are the high quality specific requirement specs, requirement sentences. But it actually, if you look carefully, there is a syntax. Let's show it explicitly. It starts off with the subject of the requirement. What is the subject? The imperative, typically shall, but there are other ways of having an imperative. You might use the Moscow system. An action, this is going to be implemented or sorted, used, installed, and then an object, which is the object of the action, and then often there was a condition throughout the life cycle, etc. So those are the components of quality requirements, the syntax that we can use. And I remember it was in the year 2000, just after this was published, that I read this paper. And it pointed out there's where you need to use actors from your stakeholders, actions and objects you get from your model-based systems engineering, performance requirements, triggers, etc. And when I read that you could actually analyze requirements using this type of linguistic elements, it transformed how I developed requirement specs. So how are we going to do this? Well, I use a template. Now, there are other templates, I know, but this is one I start with. So the actor, taken from the stakeholders, should, shall, typically shall, but there may be others, do an action on the object. What's the object of the sentence? To the output. Where's the output going? Another typical actor from the stakeholders. A performance need. Is there any triggers? When does this happen? Constraints, that's optional. Sometimes you have constraints, sometimes you don't. So that a rationale, and this is important, the description of value or benefit that is achieved. I think that's really important because it helps for communicating understanding. Why is it you want this particular thing? Well, that's the value, the benefit that will be achieved if we have it. Here's an example. The coolant pump shall move the coolant to the heat exchanger rate of 500 litres per minute when the coolant temperature is over 120, unless coolant temperature is over 130, then 600 litres. So that hot coolant is taken away from the engine. That's what you're trying to do. Get hot coolant away from the engine. Now we can then analyze these into its linguistic elements. And it's amazing when you do this, you can see commonality. Here is a compound noun, verb, a noun, another compound noun. Here's a fluid rate with a particular syntax. There's another fluid rate with exactly the same syntax. Here's temperature triggers with exactly the same syntax. Different content, different content, different triggers, but the same syntax is used. And this is important. Now, as I said, it's not the only syntax for a quality requirement. There are others. I think ears goes into it quite a lot, but I'm just going to analyze this particular one. So once we've got our syntax analysis, how do we do semantic analysis? Right, to explain about semantics, I'm going to use just 3 words. So the 3 words, book, library, and you can order any 3 things in 6 ways, but only 3 are syntactically correct. They are a library book, a book library, and book a library. So that's syntactically correct, but is it semantically correct? In other words, the word book, I want to refer to it as an object, a thing, a book. I don't want it to be a descriptor, a type of library. Similarly, I don't want to be an action that is acted on the library. Okay, so it's syntactically correct, but semantically, only one of these 3 is correct. So you could measure one simple sentence. I want to book the book from the book library. Okay, let's try and analyze this. So our phrase, we've got our 3 syntactically correct, but these 2 are semantically inconsistent. The word book is not being used as an object, it's using as descriptor or action. So this scores a 1. This is the only valid one. Now there are 3 other, which are all syntactically incorrect. Library, a book, library, booker, book, library, The last one there is both syntactically and semantically wrong. So it scores a 2. Book the book from the book library. This is the important thing. It's syntactically correct. It follows the textual analysis. It gets through the first 2 checks, but it fails dramatically at being semantically inconsistent. So I want to reserve the book from the document library. That's syntactically and semantically consistent, and therefore as English speakers and non-English speakers, where English is not your first language, it's much clearer that that's what you want to do. So how do we then bring these things together, the terms, the syntax, the semantics? How do we verify that meaning? Well, here is a sentence. The temperature sensor shall measure the coolant temperature, a minimum rate of 10 measurements per second. Very clear. We now block it out. What are the various linguistic elements that we have here? We've got a temperature sensor, which is of type temperature sensor. We've got measure, which is a sense. And there's a relationship between temperature sensor and temperature. A temperature sensor senses a temperature, and we've got them in the correct order. So we can analyze this with a model of language. This is our model here, and we're comparing the model with the actual, and we analyze it and see that it makes sense. That's how we use the AI as a language model. In fact, GPT chat is actually a model of language. That's all it is. And this then allows us to measure quality. But before we can do that, we need some rules, because it's not just we've got our classified terms, we've got our syntax and our semantics. We can now check meaning, but what makes it good? So the rules that we're going to use are the INCOSE rules in the guide for writing requirements. Now, this presentation was in 2018. There's been a couple of updates of the guide for writing requirements, so this may not be completely up to date, and I apologize, I haven't updated it. So let's have a look. Here is my universal guide for writing requirements. It's very simple. Avoid the bad, enforce the good. What do I mean by bad and good? Well, it's quite simple. Let's look at rule number 1, indefinite articles. So it's the INCOSE guide says, avoid the indefinite article, and they give an example. The system shall provide a time display. That is not a clear requirement. Much better is enforcing the definitive article. The system shall display the current time. And how do we measure this? Well, for avoid, we put in some conditions. We say that if A is 1 or more, that's bad. If it's less than 1, in other words 0, it's good, green, excellent. That's the avoid metric, but you've also got to have the enforce metric. Have you used the correctly? And we can see that this sentence, yes, we've got 1 or more the's, and so it passes the enforce test as well as the avoid. And you need both. You need the avoid and the enforce rule to determine the quality of the requirement. Let's look at a different one. In precise quantifiers, here's a list of those things you should avoid. So the information system, display the altitude approximately, it's there. What we should have said is something like quantify it. We shall display current altitude plus or minus 1 meter. We have a very, there's an example from the coolant, and it's the same pattern. If less than 1, in other words, 0 of these is good. Here, you need to have at least 1 of these quantified performance criteria for it to be good. Now, it's not just a binary good, bad. We can also think about having a medium. Now, rule 26, pronouns. You should not have pronouns, so the controller shall send the driver his itinerary for the day. It shall be delivered at least 8 hours prior to his shift. These pronouns are not particularly good at being clear and consistent. So we need to actually the name of the stakeholder. So we can check that we've got stakeholders. If there are stakeholders present in our requirement statement, we can check that they exist. So the controller shall send the display itinerary for the day to the driver at least 8 hours before the driver's shift, not his shift, the driver's shift. But my experience is that it's not the first pronoun that causes problems, it's the second one. Typically the first pronoun, so the controller shall send the driver his itinerary. It's very clear who that his is applying to. So therefore, I'm going to apply a 3 range quality requirement. I'm going to say if I've got none of the avoid, that's good. But if you've got 1 of them, that's okay. That's a medium. But any more than 1, 2 or more, no, that's poor quality. So these are the rules. This is how we're going to measure them as high, medium or low. Let's actually see how that works. Now, I'm going to give you a graph now of the number of requirements written and reviewed at the end of each of the month. I'm only going to look at one of the specifications. We did it for all of them. but I'm only going to show you one because I've only got limited time. And so we started on the 11th of December 2014 with a whole bunch of requirements. They grew over the 6 months that we were developing requirements. And in this one particular spec, I won't tell you which one, we ended up almost about 450 requirements, all very interesting. Yes, it's a very simple, typical graph that you would see for this type of work. Now, what's the percentage of requirements at each quality level for each month? So when we started, a high level, we're at 45%. And by the time we'd got to the end, they were up almost, they were just over 75%. We'd also shrunk the medium, but we never got rid of all the bad ones. And that's okay. Don't aim for perfection. There are times when, yes, you have to determine the risk of going forward with some low quality requirements. But what this does, identify the risk requirements. If they are poor quality, people may misinterpret them. And therefore, we need to quantify that by looking at carefully those responses to those requirements. So don't aim for perfection, but at least understand how the quality is evolving. Now, that's a very broad brush. It's much better if we look in detail at the various rules. And this is one of the baselines. We can get a report out in Excel of the a nice pie chart. But what I found interesting is this is high, medium, and level per rule that we were testing at that particular time. And what this means is that we can look at the most frequent error, uniformity of language. Terms were still getting through that people were using which were not in our library of controlled language, and we had to go back and substitute those. That's a relatively easy thing to do. Look, least frequent error, vague adverbs, we got rid of all of them at this particular stage, 100% high quality. And I find these individual rule metrics much more easy to actually review and push in certain areas to improve the quality of the requirements. Now, the project manager wanted an overall number for the whole of the specifications, and here's the formula for it. And I'm afraid I'm not a fan of this at all, because just because you've got a number that covers the whole of the requirement spec, it doesn't focus in on where the problem lies, and it doesn't tell you how you can improve your requirements expression. So I don't like it myself. So it doesn't give a true, an accurate picture of exactly where you are, how much work needs to be done. However, you can then plot the number of requirements written and reviewed at each quality level at the end of each month. And this was very telling. This is how it improved. And you can see very clearly that there was a big jump here. I'd explained and trained people in we'd done our stakeholder analysis, we'd done our context diagrams, we had our controlled vocabulary, and notice how they were much more productive, and which followed on for these various months. We had a good sustained effort. We got within a month of the end and we had a purge, and we were able to really improve our high quality. Notice we tried to shrink as far as possible the medium, and we were still stuck with some poor. In fact, if you notice, it drops down a bit because some of them were so poor, I deleted them completely. I decided that it was a far too great a risk going ahead with some requirements. We just simply asked the potential suppliers, questions about the capabilities in those particular areas. I deleted requirements. So very successful, but was it worth all the time, money, and effort? Well, what's the return on investment? So I don't know if anybody of you are familiar with COSISMO, the systems engineering cost model, but I've been aware of this for quite a while. I did work on both COSISMO and COCOMO beforehand, and the size parameters that drive the systems engineering costs, well, they reckon for system requirements, are they easy, nominal, or difficult to fulfill? And I know this is very crude, but I think it illustrates the point. If we equate the high quality with easy to understand, the medium quality with nominal understanding, and the high quality with difficult to understand and therefore difficult to cost. If you don't understand the requirement, how can you cost it? Let's look at the very end and do the same categorization. High quality are easy through to low quality are difficult to understand. We then end up with an estimate of how many months to do this work. And there's the effort estimate. And now we can actually fill in the individual months, and we can have a graph that shows us the overall costs in if we'd stayed with if we'd only kept the initial one, or implementing the higher quality requirement set, the final state across the 6 months and the initial state. Notice we've got a large saving here. Now, I believe that's due to increased efficiency. Do you see that kick up after the first month? We were much more efficient in our specification work, less misunderstandings in writing requirements. There's another important kick here. Second large saving due to easier verification, fewer iterations. We started having to do a lot of iterations, but those plan, do, check, act, those sprints, if you like, they got a lot easier because we were building in higher quality requirements. And of course, we ended earlier because we didn't have all that rework to do. And again, there's a third large saving. So on this crude measure, and I accept it is crude, there's a potential of a 40% reduction in the cost of document production. That's what we're measuring here, the cost of writing those large documents. And I think that we did it, I think we produced better documentation, but we also did it quicker. What was the result? We had a time scale, 6 months to do it all. We achieved that time scale. It was close. It was blooming close, but we got there. Very importantly, we increased the capability of the staff. This way of working was brand new to them, and they really caught on early. They saw the benefits coming in very early, and now this way of working is now embedded within that department. Key, there's a common understanding between the stakeholders and the stakeholders' need, which is expressed in the system requirements, which is communicated to the bidders. They understood what it was that we were trying to buy. And at that bidders conference, basically they all said and appreciated the high level of all those technical specifications. Every one of them noted it, of those 4 bidders. And the procurements conference, when we actually chosen the bidder, and we sat them down and we went through individual requirement one at a time, and we got their individual agreement. Yes, my system will do that. Yes, my system. We had 100% agreement to the technical part of the contract. Here is the final signing ceremony between the Minister of Defence and the Hanwha, who were the delivery, the K9 Thunder. There you can see in front of them the documentation. Let's just zoom into it. About half of that is technical. The other half is legal and contractual. And we achieved agreement 100% on the technical. Took a couple of days. The arguments over the technical and contractual and well, they just went on and on and on. It was, yeah, it was very clear that we were doing a lot better. How am I doing for time? I've overrun, I think. Anyway, do we have time for a video?
How long's the video, Simon?
1 minute and 20 seconds.
Go on. Let's do that, and then we'll just have a couple of very quick. I mean, you have overrun, but it's been a fascinating presentation. So I'd like to see the video. So, and I'm in charge. So there we go. So.
Okay, this is one of the guns. This explains what's happening out in Ukraine. Did you notice the camera jump? So we've got to get the second one off. And then the third one. So this is the problem. You fire a shell at somebody, they're going to detect it. because when you'll see in just a moment, you'll see the shell detection radar, the radar that detects the shell going out. But first of all, you've got to get your vehicle ready. There's a big stabilizer at the back. 3 of the crew are in. There's a 4th just on the right-hand side, which you'll see in a moment. They're getting ready to shut the door. There's the 4th and 5th member. He's got to jump in. He's got it in. And you're clearing with 20 seconds of the 1 minute and 20 seconds. It's about a minute. Now, on your left-hand side, here is the shell detection radar. So we've detected going out, which means the enemy's got this radar detecting it coming in. They've got to then back trace the trajectory of the shell back and work out where you are, and then they fire their gun at you. But you're away in under a minute. That's how you survive in Ukraine. Thank you very much indeed for listening to me. I apologize for over. So
Simon, thanks very much. That was fascinating. The only thing that's mildly concerning me is that if you were holding the camera and all the guys jump in the van and leave before the missiles come in, you weren't in the vehicle. So
no, absolutely not. No,
so
no,
they just left you behind.
This was this was not a this, although it was a live fire, it was into the test area. So
right, okay, so and you're still with us, thankfully. So excellent. And some nice plugging of the book. Well, we have overrun, but it's one of the nice things about these sessions is we can overrun a little bit. There's nothing coming up next. So if anybody's got any very quick questions that they'd like to type in, otherwise I've got a couple of comments. First of all, it's really good to see some actual numbers put on something, Simon, in terms of what you did at the end. And put in pound notes. I know they were dollars or whatever. It's very rare that we see that, and it's great that we have all these different techniques. But how often do we see actual? And I appreciate you said, with full disclosure, they were quite crude measurements, but they were measurements and they were valid. And I think that was really good. Right, we've got a couple of questions. We got one from Christian Nestler. I'm not sure where AI was actually used here. Perhaps I got it wrong, but aren't these deterministic checks against the guidelines with fixed criteria?
Okay, so to be exact, it was computational intelligence rather than artificial intelligence, but actually vast numbers of the AI products on the market are not AI. They are computational intelligence. Okay, most of it is stupidity. I asked ChatGPT, I said, would you pass the Turing test? And it came back and said, I'm a model of language, so no. So ChatGPT is not AI, it's a language model, and it's a computational intelligence, and that's what most of the AI is today.
Yeah, I would also say, Simon, as well, that natural language processing is generally accepted as a form of AI as well. And I appreciate the, yes, it is deterministic and whatever, but it's generally accepted as a key part of AI, if nothing else.
Absolutely, so. And in my view, it's for this particular method, this particular application, it's very important that we don't have a training database of good requirements which are fed into a machine learning, where you then give in your other things. Who said that the data in was any good or not? What was the measure of quality of the input of the training set into a machine learning? I asked all the manufacturers who've got these type of things, would you share with me your database of what you think is good? And they've all said, oh, no. You can't see that. That's proprietary. This method is non-proprietary. Anybody can do it, and you know what the results mean.
Yeah, excellent. I couldn't agree more, Simon. And as you know, you mentioned it in here, model-based systems, anything to do with model, a model is only as good as the information that's put into it and the trust and the confidence you can have in that. So, yeah, great. There's lots of people saying thank you very much. There's a couple of people saying, will the presentation be shared? Yes, it will. We'll do that via when it gets put up onto the Incozy website or whatever happens there.
Yes.
So Simon, a fascinating presentation. I enjoyed it the first time. I enjoyed it a lot more the second time. I think we had a bit more time this time.
Yes.
And like I said, it's nice to see a bit of a retrospective as well. That was 5 years ago. You know, where are we now? And yeah, fascinating. So on behalf of myself and I'm sure all the participants and in Cozy UK, Simon, thanks very much. It's been a pleasure to listen to you again. Okay.
Thank you for the opportunity.
Okay, cheers then.